Okay, before jumping into the demonstration, I thought it'd be best to do a brief overview of the system. So, if you saw the PowerPoint presentation, you maybe already have an idea of how the system flows. We're just going to go over it one more time for the sake of the demonstration. So, the ETL part is orchestrated via a single app. Uh, on the app, you can load your queries via text file, or you can write them in directly. But for me, it's easier to just write them into a text file and then load the text file and run the queries after that. So starting off, once you start the ETL pipeline, the first step is you'll send the API request to three databases for academic literature, those being OpenAlex, PubMed, and Scopus. For the purpose of the demonstration, we're going to skip Scopus because it has some strict rate limits, which significantly slows down the pipeline. So once we get our responses back from these databases, uh, generally we collect metadata from these databases, but there is more metadata in Crossref that can enrich the original metadata, such as citation counts, whether an article is retracted or not, country of origin, stuff like that. Once we're done with the metadata enrichment, we download the actual PDF file. If it's open access, we can access it by giving the DOIs to paywall, which then looks for the open access files. Typically, we're only retrieving about 30% of the articles that we initially identify from the uh, databases like OpenAlex, PubMed, and Scopus, but um, that's something we'll work on in the future. But after you get your PDF, now you have your article metadata plus your PDF. So next you populate your Zotero library with the articles that you found, the ones that you could get the PDFs from. You have the option to also upload the PDF file corresponding to the article metadata, but that also has some strict rate limits, which is pretty slow. So most runs I usually skip that. After you're done syncing with Zotero, then it goes to the text extraction using docling and small docling. I replaced their code formula model with their small docling model because the code formula model was pretty bloated and always had problems. But once you extract your text tables and formulas, it gets exported as Markdown. The Markdown for each article is then fed to an LLM, and the LLM does the field extraction. There's multiple fields you can extract. You can select many fields from the GUI. Um, Once that step is done, it goes through LDA topic modeling to identify the themes within your corpus and categorizes your articles based on that overarching theme. Then before it goes into the graph database, it goes through field standardization and normalization using sentence transformers for this. I'm using all many I don't know all many something. Um, what this does is it unifies the data extracted by the LLM to something that's within our dictionaries. I have 28 dictionaries with about 9,000 synonyms. So the sentence transformer will try to unify what the LLM extracted to what we have in our dictionaries. Once that's standardized, it goes into the graph database. And once we have our data in the graph database, that's usually where, for me, that's usually where I stop because from the data from the graph database, I can do some cipher queries to get the data I need, such as metrics specific to any kinds of studies or balloon types or machine learning algorithms. Uh, but once you send those cipher queries in, you get the response back. And then to continue on to the actual RAG step, first you manually review all the articles you got from the graph database. Once that's reviewed, uh, You start the actual RAG process. The first step is you send your corpus into Quadrant. It's already in Neo4j, so all you gotta do is query it. Uh, you send a query to your LLM. The LLM reformulates the query and generates keywords. Then those keywords in the formulated user query are used by the system to find the best matching chunks. Then it goes through a what I call an agentic chain of thought iteration step, which includes a QA step, and here it'll produce an output, and then it'll check its output against the original data to see if it's making stuff up or attributing metadata to the wrong article. And if everything works, then we get our output, and yeah, we move on from there. All right, next we will move into the actual demonstration. Good afternoon, my name is Alex. If you're following up from the earlier PowerPoint presentation, this video will be a brief live demonstration, or not live, but a recording of the demonstration of the ETL part of the system. So getting familiar with this screen, what we have here is now here we have Zotero. We have this open so you can see how the extracted metadata from the articles gets automatically integrated into Zotero. Up here we have Neo4j. Once the data gets stored or sent into Neo4j, you're going to see this part here get populated with the different nodes and relationships identified by the LLM. And over here you just have basic performance measures of the system to make sure that we're not frying anything. So the system is built on Python. To start it, you run a command from your bash. So once you run your bash, you get your GUI up here. Going over the basics, so the ETL phase has 7 distinct steps. You have the acquire phase or stage. This is where you query PubMed, OpenAlex, and Scopus to get your articles, DOIs, and metadata. Then you download the PDFs via Paywall. After that, you send the data to your Zotero account. Then the PDFs get processed by Docling. Then you do field extraction using an LLM. For the purpose of this demonstration, we're going to be using OpenAI's LLMs, given that if I were to use Qwen, it would take approximately five hours to finish the step. And then we go into topic modeling, and then finally loading your data into the knowledge graph. So configurations, basic configurations for Docling. First, you need to specify what GPUs you want the system to acknowledge, given that the GPUs I wanted to use are the two RTX A6000s. Those are 1 and 2. Here I write 1 and 2. This is how many workers I wanted to use. 12. If you don't have GPUs like these, you can always fall back to CPU, but if your system can handle it, stick to CUDA. Then on paywall, for on paywall, you got to give it your email address for the HTML header. Same for PubMed, OpenAlex, and Elsevier. For Elsevier Scopus, you actually have to give it a you actually have to request a API key to use their creator servers. Zotero integration. Here you specify your library ID, the type of library it is, your API key you have to get from the website, and the this is the collection it's going into. So I want it to go into my demo collection. So this is the demo collections ID. And here you select what kind of citation style you want. I usually stick to APA 6. This is your OpenAI API settings if you're using OpenAI. And down here is where you select your field extraction for the LLM. This is what I refer to when I say it's domain agnostic, because here uh, you can basically select all of these or select a few of these depending on what your research question is. For the purpose of this demonstration, we're going to stick with the ones already selected. Topic modeling. Here you can set uh, your pre-processing steps, what you want to remove from the text, how many workers you want it to use, how many models you want it to use, and once it generates the dominant topics, generates keywords, you use OpenAI's LLM again to generate concise, human readable labels for the topics. Then you set your hyperparameters. We're going to stick with these for the demo because anything more than these parameters here, they equal about 680 combinations, which would take about 10 minutes to finish. And you might be asking, how does the LLM know what to extract? Are you giving it as just these field names? Whenever we send the queries to the LLMs to extract the information, we also we're not just giving it the name of the columns to extract, but we're also giving it explanations as to what each field means, so they know what to better look for. So for example, if we want to get the machine learning methods described within an article, we tell it to identify the ML algorithms, the model type or AI techniques used within that article. And then these are the selected columns, which reflect what the user selects on the GUI. And then all of these are all the metadata columns, which get saved following the LLM's field extraction. And for the knowledge graph integration, we use SBERT, which is the semantic embedding model. The way it knows how to give each field extraction coming out of the LLM extraction, how to categorize it, is that we have these dictionaries. We have about 27 dictionaries, approaching 9,000 synonyms in total. So once the LLM provides the extraction for a field, SBERT will try to unify it to one of these unification synonyms for whatever field it was extracted to. So going back to the GUI, here you can either type out your search queries or you can load them from a file. We have all these queries here, which are related to ozone and health effects. Our data source, that's the database we want to query. We can do PubMed, OpenAlex, or Scopus, or we can do them all. For the purpose of this demo, we're going to stick with PubMed and OpenAlex because Scopus has some really strict rate limits, which make the process a lot slower. We want to make sure our citation style is APA 6. We're going to stick with 120 articles, and all our steps are selected. So from here, all we do is run the pipeline. The video will be fast forwarded to the end, and let's begin. All right, and we're back. So as you can see, it went through the entire 7 stages in about 30 to 32 minutes. We got all our outputs that we were looking for. We got our stuff sent to Zotero, and here we can see the nodes that got sent to Neo4j and the corresponding relationships. So taking a closer look at what Neo4j shows us. So say we want to look at let's look at a couple of nodes. Um, Say we want to see what kind of machine learning methods we have. You just click on the nodes. So we have these right here. So then we look at relationships between articles that use ML methods. From the 100 articles that were sent into Neo4j, these are the only relationships we have for machine learning. We zoom in. This study here used Profit, which I'm assuming is a custom neural network. All these articles here used neural networks unspecified. This article here used gradient boosting machines. This study used LSTM networks. And then most of these articles use random forests. So if we want to run specific queries, say for example, we want to know how many articles are missing their study type. Well, first let's see what kind of study types we have. So we have meta-analysis, life cycle assessments, case studies, simulation modeling studies, research articles, cohort studies, ecotoxicological studies, etc. But we're interested in knowing how many are missing their study type. So we run a little query here, match articles where they do not have a study type. We have 17 articles missing a study type. What about articles missing a pollutant term? We have 9 articles missing pollutants. What about articles since our research topic is on ozone and heart disease? How many of these articles do not include heart disease? 22 out of the 100 do not include heart disease. So how many of these articles are missing machine learning methods within their text? 88 are missing their machine learning method. So now we run a combined query of all the missing nodes. Out of a total of 100 articles, 17 missing the study type, 9 missing their pollutants, 22 are missing their heart disease, and 88 are missing their machine learning method. And if we want to look at the articles missing all 4 nodes, we have 5 that do not have any of these nodes. So what we're interested in is studies that do have machine learning methods, heart disease, and ozone as a pollutant. So we have to run a more complex query. And this gives us all the DOIs that match our query. Given that this was a small demo of 100 articles, we don't have much information. Of course, random forest will always be the most popular machine learning method. So what we do from here is we have these DOIs, so we export the this final query response as a CSV, and in the next part, I will show you how we use these DOIs to filter the main data set for the articles that we're interested in via the Flask app. Thank you. Alright, so picking back up where we left off, some may ask how exactly I'm using this to, or what the, how does this tie into life cycle assessments or whatever. So a benefit about knowledge graphs is that you can get the metrics back out from DOIs. So any metrics that were identified and extracted during the field extraction phase, that data gets saved and it also gets uploaded into the Neo4j knowledge graph. Um, so for example, if we want to get some metrics from articles that have DOIs, we run a simple query, and this gives us an example of the kind of metrics that we have for all these articles. You get a couple of columns. You get the metric name, the value, and the unit. Given that this was a small sample of 100 articles that was uploaded, there's not going to be much useful information in here. But from this query, it looks like there is 1,400 records. But if we want to get a little bit more specific and get metrics associated with different study types, for example, get the metrics for cohort studies. And here we get a sample of some metrics associated with cohort studies. And there is only one life cycle assessment study identified or uploaded. So for the one DOI we do have, it gives us these metrics. Not much, but if we had a bigger data set to work with, there'd be a lot more useful information. And you can also add additional columns here, so you know what you're working with. Okay, moving on to the manual review using the Flask app. First thing we got to do is we go back into VS Code and we run this Jupyter cell, which will filter out the main data set by the DOIs we exported from Neo4j, and we'll create a new new feather file. So we run that, and next we got to open a bash terminal. So here we get a small sample of the 7 articles that are out for review. What you get right off the bat is you get the DOI for the article, so you can go straight to wherever the article is hosted, and you also get a link to the PDF that's stored on your disk from the unpaywall phase. Sometimes the docklink extraction isn't the best. It struggles with tables that are oriented sideways or full page tables, so because of that we got this PDF fallback. The main point of extracting the text as markdown is to make it readable by the LLMs, given that they can't access the PDFs directly, and if they could, it'd be pretty resource intensive. But what you do in this Flask app is you go through the articles, and if you find something you like or something you don't like, you can write your notes in here, uh, and then you move on to the next article. Same thing here, you would review your article, go through it, look at all the tables and stuff, and if you need to look at the, oh, here's one example, this table wasn't extracted properly, so here you would fall back to the actual PDF, then you'd write your notes. And during the field extraction, the LLMs will give you a QA note if there's anything of note with the article. We embed that right at the front, so it's the first thing you see. So it's the first thing you look out for. Um, and then once you're all done, you can just shut down, um, and that's it for that. Uh, next, next we're going to look at the topic modeling results. Um, for topic modeling, we get a visualization that's built after the topic modeling step. To see that, first we got to generate the visualization, and the visualization was sent to this folder, so we navigate there. Got sent to our folder here. And here what it gives us is basically all your topics that were identified. So I think it produced about 30 topics for our paper or for our corpus. And whenever you have these circles overlapping like this, it means that the topics are more related. If they're further away, they're more disconnected. Up here you see the keywords, or the top keywords for your visualization. Alright, but yeah, this is basically to assist in the review process to see the dominant topics within your corpus. Following that, we can jump into the actual RAG demonstration. So for that, we can change our directory again. And from here we run the main demo. Right now it's embedding the articles and uploading into Quadrant. So once it's all loaded and stuff, here you can start asking your questions. Something related to our corpus, given that it was on ozone and machine learning and CBD, we can ask it something like so once it gets the query, it's going to reformulate it. Then it's going to query Quadrant and Neo4j, and Once it's done with the query, it ranks all the chunks that were identified via quadrant and Neo4j. So these are ranked based on their reciprocal rank fusion, and these are just small snippets of the chunks. So from here, probably fast forward a bit until we get the response, if it takes longer than a minute. So the reason why this one is taking a bit long is because during the agentic step, one of the LLMs noticed a problem with the output here. Sometimes the LLMs are pretty lazy, and they'll say something like instead of giving us the metadata like we ask it for, um, structured correctly, they'll try to take shortcuts. So then it gets caught by the QA or before it gets to QA, it gets inspected. So then the LLM will create a prompt telling it to regenerate and why it needs to regenerate, and then once it redoes the response, it'll get checked again, and if it's all good, we get a response here. And what we get is our observations. So these are the all the observations the LLM made corresponding to the user query, and this is all the metadata associated with the observations. And section B, that's where it explains its thought process as to why these observations match the user query. And then section C, that's your provisional answer. That's the actual response from the LLM. And down here, you have the agentic reasoning telling you why this answer is correct. And then after that, you get the QA. QA signs off on it. Well, like just imagine it's a QA LLM working in an office, signing off on the responses. So this response was good. Next, we want to try a query that is not reflected within our corpus. So some might say that, well, how do you know it's not just making up information? If it's not something that's in the data set, how do you know it's not going to just make something up or hallucinate? So to address that, we can ask it a simple question that's completely off topic. For example, so it gives us the response, basically saying that there's nothing within the data that talks about dark chocolate or cocoa products and improved cognitive function. So these responses and all the metadata, they get saved to a master JSON file. So to view that, you just gotta exit out of here. Then we go back into VS Code and we look for that export file. So this is when we started our queries. It saves the user query. Sometimes the LLMs will put a bullet before section A, which messes up the parsing. So then this observation, it's treated as an observation, but it's really not. For actual observations, like observation 2, which is actually observation 1, it saves all the metadata, and then it'll look at the in-text citation and full citation and all the other metadata and compare it against the initial data set to see if it matches. Here you have the metadata matching scores. Full citation, that's almost never 1.0 because the LLMs are lazy, and it's a long string, and it's typically the case for all the full citations. Yeah, this is the query saving and the metadata matching step. In the future, I'm going to set a threshold where if average score falls below 0.8 or 0.75, the response will be rejected automatically. But as far as the demo, this concludes the demo. Thank you for watching this video. If you have any questions, please send me an email. Thank you. Have a good day.